Very good afternoon to all of you. My name is Prakash Chandra Gupta. This paper is submitted on 4th International Conference on Electrical and Electronics Engineering ICEEE 2023, and paper title is Chaos and Multistability in Fractional Order Power System, Dynamic Analysis and Implication. Paper ID is 4666. Track 1, Paper Generation, Transmission and Distribution. The author name is Prakash Chandra Gupta and Piyush Pratap Singh. Outlines. These are the few outlines which I will cover in this presentation. First is introduction. Second, method to analyze nonlinear behaviors. Third is mathematical modeling of three machine infinite bus power system. Then dynamic analysis of three machine infinite bus power system model. Then conclusion and future scope. Then references. Introduction. As it is known that the most of the practical system which exist in the universe are nonlinear in nature. While we analyze the system, while we analyze this system in the set of nonlinear equation, we can solve it through nonlinear algebraic set of equations. So power system is itself a huge complex model, and while we analyze the power system through some MATLABs and software related things, then I have to be write this power system equation in term of algebraic equations, non-linear set of algebraic equations. So it is very interesting as well as challenging. Challenging in terms of that when we analyze such complex non-linear equation, that they are required a huge computational power and computational time is required. So that is the problem, and that's why we prefer a not very complex model. Instead of complex model, we prefer here a small power system model, three machine infinite power system model. In the past, we have seen various power system models in which the chaos behavior has been studied, and it is found that the chaos are unhealthy for stable operation of the power system. Because if the chaos present in the power system, if chaos breaks, then it go very unwanted effects like voltage instability, angle instability, or sometimes voltage collapse is also possible. Along with the chaos, there are another nonlinear terms like coexisting behavior and multistability. If such kind of behavior is present in the power system, then it is a state problem of global stability, like frequently state switching. So this kind of behavior must be controlled within the power system. So in this paper, we will discuss about the presence of chaos and multistability behavior in the three machine infinite bus power system model. Method to analyze nonlinear behaviors. There are various methods to analyze nonlinear behavior in the power system. These categorize into two categories. First is qualitative analysis methods and quantitative analysis method. Under the qualitative analysis method, there are methods like time series analysis method, phase portrait method, bifurcation analysis method. All these methods are quite simple and easy to operate, but they are not enough accurate. So that's why we go for the quantitative analysis tools. They are more accurate than the qualitative analysis tools. So these are the Lyapunov exponents and Lyapunov dimension are most commonly used quantitative analysis tool to analyze nonlinear behaviors. Mathematical modeling of three machine power system. Assuming that the infinite bus node connects the three generators, machine 1, machine 2, machine 3, is shown in the figure 1, where three machines are connected, operating in parallel and connected through infinite bus bar. This is the single equation which is derived from the classical n machine model of the power system, where delta I and omega I represents the rotor angle and angular velocity of machine 1, machine 2 and machine 3 respectively. M1 represents the inertia of the machine 1, machine 2, machine 3. Similarly, D represents the damping coefficient, P represents the mechanical input power, E represents the electrical output power. Here VB is the bus voltage. Beta IB, beta IB represents the admittance between the ith machine and the infinite bus bar, and delta B represents the infinite bus voltage, infinite bus phase angle of infinite bus. This is the fractional order representation of the three machine infinite bus model which we have seen in the previous slides. So here dq represents the fractional order operator. So here we have used the Grunwald-Letinkoff GL method to analyze the fractional order. Although there are various models like Caputo's and other many model to investigate the fractional order behavior. Here we have chosen the GL method because it provides some advantages over Caputo's and other methods like smooth coefficient of fractional coefficient. So that's why we have used the Grunwald-Leitenkopp method. So this is the discrete version of three machine infinite power system, and these are the system parameters which I have considered to analyze the different nonlinear behavior. So while analyze the nonlinear behavior, we have kept all the parameter values as a constant as given values and only varied the derivative of the fractional order q and analyze the different nonlinear behavior. Dynamic response when varied the fractional order q. So this slide we show the uh, different dynamic behavior when we varied the order of the differential equation. In the figure 2, uh, we see that the this is the bifurcation diagram when we varied the q value from 0.9 to 1, and we see that the different kind of structure here like a single lines, then double lines, then four lines, then some distance and number of points here. So this is the bifurcation diagram. So to analyze this, to understand this bifurcation diagram more, so we have plotted a phase portrait corresponds with the bifurcation diagram. Here as the q equal to 0.93, this will lie somewhere in the bifurcation diagram q equal to 93. We see that q equal to 93 in bifurcation diagram in figure 2. One single line we are seeing that. So this single line represents the period 1 behavior. Similarly at q equal to 965, we see in bifurcation diagram we will see two lines. These two lines shows the period 2 behavior. When we select the q equal to 0.982, this will shows the somewhere in dense lines region. So this will shows the chaos behavior. And when q equal to 0.997, this behavior shows the multi-scroll chaotic attractor. So this is the bifurcation diagram and corresponding phase plane diagram. Okay. Correspond with the previous slide where we have a four values q equal to 0.93, 0.965, 0.982 and 0.997. We have seen the four different kind of behavior: period 1 behavior, period 2 behavior, chaotic behavior and multi-scroll chaotic behavior. So this is the at particular value we have calculated the Lyapunov exponent L1, L2, L3, L4, L5, L6 and corresponding nature of maximum positive Lyapunov exponent. In short name I have written here MLE, and corresponding dynamic behavior listed in this table. We can see that q equal to 0.982, the maximum positive nature of maximum positive Lyapunov exponent MLE is positive, which confirms the behavior is chaotic. Similarly, at q equal to 997, at this points the chaotic attractor breaks and shows the multi-scroll chaotic behavior. This represents the angle instability case. This is the case of angle instability. Furthermore, at q equal to 982, we have analyzed the dissipativity analysis. So to analyze the dissipativity with the help of Lyapunov exponent, if the sum of all Lyapunov exponent is negative, then it confirms that the system is dissipative in nature. So here we have added the Lyapunov exponent L1 to L6, and it is the sum of all the Lyapunov exponent is minus 1.46. This represents the negative value. This indicates that the system is dissipative in nature. In the previous slide, we have seen the multi-scroll chaotic reactor angle and stability through multi-scroll chaotic reactor. So here we have given the rotor angle and angular velocity for each machine 1, machine 2, machine 3. Delta 1, delta 2, delta 3 are the rotor angle and rotor angle of machine 1, 2, 3. Similarly, omega 1, omega 2, omega 3 are the angular velocity of machine 1, machine 2, machine 3. And this is the phase portrait of machine 1, machine 2 and machine 3. This shows the um, multi-scroll chaotic behavior when q equal to 0.997. Now coexisting behavior and multistability. So to see the coexisting behavior, we have first to observe the coexisting behavior, we have using a bifurcation diagram. First we have varied the parameter d1 from 0 to 0.6 and plotted the bifurcation diagram. Then we have kept all the parameters constant and changed only the initial condition. In initial condition, here figure 5, please see in caption figure 5, here three different initial conditions are written which are represented with three different colors. So at when we see from point 6 in the backward side, from point 6 to point 1, near to the point 1.5, we are not seeing any kind of different colors, uh, but from 0 to between 0.15 we have seen the different kind of distinct points. So this different distinct points shows the presence of coexisting behavior. Further, this behavior analyzed with the help of phase portrait behavior. Here, this in the figure A, B, and C shows the multi-stability behavior. Here, here we have kept all the parameter at the constant value, only varied the initial condition. Here, three different color represents the three different attractors present in the system. So this is the case A when parameter value d1 equal to 0.15, and when case B is the when parameter d1 is 0.14 and d1 equal to 0.133 represent with the figure 3. As we have here see that the three different kind of attractor, this shows that the presence of coexistence of attractor. In the figure C shows the coexistence of one chaotic attractor with two multi-scroll chaotic attractor. In figure B we see coexistence of two chaotic attractor and one multi-scroll chaotic attractor. Similarly, in figure 1, we have seen the three different chaotic coexisting attractors. So, all these slides we have shown that the presence of multi-stability behavior in the power system. So, these multi-stability behavior are unhealthy or undesirable for stable operation of power system. If the multi-stable behavior present in the power system, it can frequent switching from one stable state to another. So this is undesirable for stable operation of the power system. So it must be controlled. So conclusion. So in this paper we have discussed about the three machine in finite bus power system, which is derived from classical and machine power system model, and we have analyzed the different dynamic behavior such as period 1, period 2, chaos through period doubling bifurcation, and other nonlinear behaviors such as multi-stability, presence of multi-stability behavior in the power system. So these are undesirable, so it must be controlled. So in our future work we will control these undesirable behaviors such as multi-stability and chaos behavior with different nonlinear control techniques. So these are the few references. Thank you.